Welcome to Precalculus Algebra, and in this video we're going to study the average rate of change of a function. So I've graphed the position function. Let's go on a little journey here. So we have position, that is how far we are away from our house in terms of miles, for example, measured against time. And if somebody asked you, oh, when on this journey were you going the fastest? Well, you'd say maybe between here, call that point A in time, and right there, call that B in time. Between A and B, you're going pretty fast, right? Why? Well, because the curve gets really steep. So the steepness is measuring the speed of our journey, right? How fast we're going. And so you can see that, we're going sort of fast here, but we get really steep. That means we're a lot of miles, we're changing a lot of miles for a given amount of time, and then we sort of slow down as we get closer to B. So between A and B, we're going pretty fast. And notice that if somebody asked you where you're going fastest, you might say, oh, right here because it's steepest. So what we're noticing, first of all, is that steepness of a curve. That tells you about speed. Okay, and that's for when you have position versus time. So the steeper it is, the faster you were going. Now, if somebody said, what was the average speed between A and B, you'd say, that's hard because here you're not going very fast, but then you speed up and then you slow down. How would you find the average? Because after all, you have all these different speeds between A and B. And it turns out that in calculus, all you have to do is pick the point at A and pick the point at B, and then draw a line through those 2 points, like that, and then calculate the slope of that line. And it turns out the slope of that line will give you the average speed between points A and B. That's kind of amazing, right? Think of all the different speeds you're going on that trip right there between A and B, and if you want the average, all you have to do is take the slope of that line. Now the same thing is true not if you have just position versus time, but any function on the y-axis versus an independent variable x, okay? So we're going to study the average rate of change of a function, and all we have to do is calculate the slope of that line. Let's go ahead and do that. So let's say you have a function f, and I've picked 2 points A and B on the function, and let's say you're interested in the average rate of change of f over the interval AB. Just like before, f isn't changing very fast here because it's not very steep, but it's changing really fast over here, right? Because it gets a lot steeper. So what's the average rate of change when you consider all the points between A and B? What's the sort of average rate at which it's changing? All you have to do is draw in the secant line, what's called the secant line between those points. Okay, and take the slope of that line. And so to do that, what we're going to do is we're going to identify the y-coordinate at A. So if this is the function f, at A we're going to call this point right here f at A. And then if this is B, call that point there, call it f at B. And if you want the slope of that line that I drew in, that's called the secant line, all you do is you take this distance, right? So that's f of B, take away f at A, and then you divide it by this distance right here. So that distance would just be B take away A. So the average rate of change is defined to just be f of B take away f at A, and then divided by B take away A. That's the definition of the average rate of change of a function over a given interval from A to B. And we notice from our discussion that all it happens to be is the slope of the line between the 2 points. So it happens to be the same thing as the slope, which we're writing as m, of the secant line. So a secant line is simply a line that cuts the curve in 2 places. So it's the slope of the secant line between the points A and B. Okay, and that's the definition of the average rate of change of a function. Kind of amazing, right, that you can get the average rate of change just by calculating the slope of that line. It takes into account all these different rates of change, all these different steepnesses along the curve, and it averages those, and all you have to do is take the slope of that line. Okay, let's see an example of this. Let's find the average rate of change of this function, f of x equals 3x squared plus 2, which I graphed here, part of it, over 2 intervals, first from 1 to 2, and then from the interval 1 to 4. Okay, so for part A, right, so we're after the average rate of change. I'm going to abbreviate that as ARC from the interval from 1 to 2. And by definition, that's just f of 2, take away f at 1, divided by 2 take away 1. So all you do is you evaluate the function at the end, subtract off the value at the beginning, and then divide it by the right point, take away the left point. So let's see, f of 2 is going to be, plug that in, and you get, it's going to be 14. And then you subtract off f at 1, and you plug that in, and you get 5. And then we're dividing by 2 take away 1, which is 1, and that's equal to 9 over 1, which is 9. What that's telling you is that, on average, between the interval 1 and 2, every time you go to the right 1, you go up 9. That's the average. That's how quickly sort of y changes with respect to x. It's the slope of the secant line between the points 1 and 2. By the way, this should have been a closed bracket here. So it's from 1 to 2, but with closed bracket on 2. Let's try that again. Okay, and let's do the same thing then, but now over the, let's calculate the average rate of change of this function over the interval from 1 to 4. And that's going to be, f, by definition, f of 4, or f of 4 take away f of 1. So f of 4 take away f of 1 divided by 4 take away 1. And if we plug in 4, what do we get? Well, it's going to be 16 times 3 is 48 plus 2 is 50. Take away f of 1, which we calculated before as 5. And then divided by 4 take away 1, which is 3. So we're looking at 45 divided by 3, which is 15. Okay, that's greater, right? The average rate of change is greater over the interval 1 to 4 than from 1 to 2. Why? Well, if we look at 1 to 2, when we draw in the little secant line, so from there, if we draw in the secant line from there to right there, okay, the slope of that line is 9. So the m is equal to 9. That's the slope of that line. That's for the first part. But if we draw in the slope of the line from 1 to 4, right there, okay, the slope of that line is 15. So why is the average rate of change greater for the second one? And the answer is because it's not just because you chose a longer interval. Look at the curve. It's not moving very fast. It's not very steep right here, right? But once you get beyond 2 seconds, look, it starts getting steeper, 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 steeper. So it's going a big rate of change right here, right? The steeper the curve, the larger the instantaneous rate of change. So when you average all those rates of change between 1 and 4, what happens is when you start getting from 2 onward, you start getting really fast rates of change getting averaged in. And what does that do? That makes the average larger. So between 1 and 4, you had a larger average rate of change, 15, than just between 1 and 2, because you were incorporating parts of the curve that were steeper. Okay, and that's how you increase your average rate of change. Just like if you were driving somewhere, right? And let's say the journey took you 5 hours, and you sped up the last 2 hours. Well, that means you're going to increase your average speed because you're including a part of a journey with a steeper part of the function, if you will, right? You're putting in greater speed, so that increases the average. Okay, and one more point about this is that the average rate of change does not always have to be positive. Let's see an example where it might be negative. So let's calculate the average rate of change of this function over the interval from 1 to 3. So just like before, the average rate of change is defined to be f of 3 take away f at 1 divided by 3 take away 1. And let's see, f of 3 is going to be, if we plug that in, we get 9 times 2 is 18, take away 30, which is negative 12. And then we subtract off f at 1, which is negative 8. And then we divide that by 3 take away 1, which is 2. So we're looking at negative 12 plus 8 divided by 2, which is negative 4 over 2, which is negative 2. Okay, so what's that saying? Well, that means the slope of the line between 1 and 3, so where are we? Well, 1 puts us right about there, 3 puts us right about here, and if we draw the slope of that line, okay, the slope of that line is equal to negative 2. What's that telling you? Well, it's telling you that the function, on average, between 1 and 3, it dropped. The average rate of change was that you were dropping 2 units every time you increased 1 on average. Now we know that you're dropping really fast here, and actually over here it looks like you're increasing. But on average from 1 to 3, if you calculate all those instantaneous rates of change, on average you dropped 2 units every time you went over 1. Okay, one more point, that in all these examples, the numerator, just the numerator by itself, so in this case f of 3 take away f of 1, that's referred to as the net change. So the numerator, just by itself, not the denominator. We know the whole thing is called the average rate of change, but just the numerator, whenever you do this, is called the net change. So in the formula, generally, f of b take away f of a, you'll see that referred to as the net change of the function between a and b. Okay, and then when you divide it by b minus a, you get the average rate of change. Okay, until next time.